Guten Tag. This is episode 7, 2026. We're talking about JSON structure. My name is Clemens, and this is Subscribe. Today I'm introducing JSON structure. JSON structure is a schema specification focused on defining data structures for data interchange and tooling. It's a pragmatic response to where JSON schema ended up in practice and the needs we all have as schema must reliably map to programming languages, databases, wire formats, and metadata systems. So let's talk about JSON schema first for a moment. The de facto standard that everybody's using today is Draft 07, published in 2018. Later drafts exist, but tooling uptake has been very inconsistent. So that's a strong signal that Draft 07 is kind of good enough for validation, and additional features did not materially improve the situation for most users. The real issue that many are facing is that JSON schema is often like inside OpenAPI, used as a structure definition language, aimed at fostering interoperability, even though it was never designed to be a data-defined language. It's purely a validation language for JSON documents. Everyone who seriously models data with JSON schema runs into the same problems. No tool can fully handle every valid schema. All tools eventually give up at different complexity thresholds. Code generation and schema derivation are inconsistent across tools because too many definitions lean on loose conventions. Types are often unnamed, weakly typed, or implicit, and constructs like one-off, all-off, and if-then-else are pattern matching rules, not structural modeling tools, and yet they are routinely misused as such. The primitive type system is essentially JSONs, with format as an incomplete escape hatch. Crossfile $ref creates brittle location-dependent coupling. JSON schema is powerful, but it's the wrong abstraction layer for defining interoperable data models, which most people find. So that brings us to JSON structure. JSON structure is a set of 7 IETF internet drafts, a core specification, and 6 companion extension specs. The landing page for the project is at json-structure.org. JSON structure is a refactoring of sorts and extension of JSON schema, even though the projects are not related, but it leans on the look of JSON schema. And the goal is not to improve JSON schema per se, but it's to build something else. It's to build a data definition language. We mandate the explicit naming of every type. Namespace support is there. Controlled reuse of types is there. A rich primitive type systems that maps into programming languages, and first-class compound types in addition to arrays and objects in form of sets and maps and choices and tuples. Everything that's pattern matching or conditional validation is pushed out into optional companion specs that you can use, but you don't have to use. So those concerns are explicitly separating the validation aspect from the structure aspect. Additional companion specs layer on things like international names, alternate symbols, units, currency annotations, further context that improves data quality and allows for better machine interpretation, including by LLMs. So here is a object definition in JSON structure core. And if you're familiar with JSON schema, this shape will look immediately familiar to you, and that's very intentional. What changes here is the discipline. The type is required. Every type must have a name. The primitive type set is expanded, as you can see here with the date. And everything is intentional. There's a subset of JSON schema. This is the subset developers actually care about, defining objects, defining arrays, defining composite types. And here we're tightening the rules and we're focusing really on those aspects. And it's also a superset in the sense that it has a richer type system. The so-called extended primitive types that go beyond the basic JSON types introduce a full primitive type system that's not just validation hints. It's fully semantic types with defined wire representations, range constraints that map to the concept of programming languages and map to the concept of databases. Signed and unsigned integers up to 128 bits, decimal with precision and scale, date, time and duration, UUID, URI, JSON pointer, binary with a defined base 64 encoding, and even float 8 for ML workloads. All those extended primitive types map deterministically to JSON base types, mostly string and number. But the semantic intent is well defined for tooling. And for large numbers, we also solve a long-standing problem that JSON itself cannot represent large numbers beyond 53 bits. And so therefore all the larger number types actually map to strings in JSON structure. In addition to arrays and objects, JSON structure adds compound types that directly match two common programming language constructs. A set is an array with a forced uniqueness, and a map is a first-class dictionary type. And that eliminates the need for an awkward, object plus additional properties modeling that aligns directly with how maps and sets exist in real languages and other serialization format like Avro. That matters because JSON structure is also built to map from and to other serialization schemas like Avro, like Proto. Another compound type is tuple. Tuple is a structurally defined like an object, but serialized as a positional array. The schema defines everything like an object, but there's a tuple annotation that kind of then guides what the order is. And that's especially useful for dense, high-volume data, such as time series data, where the field tables would be redundant and repetitive, but where the semantic guidance still matters. So tuple is effectively an object that's serialized out as an array with a guidepost that is the tuple array. Reuse is deliberately constrained. Reusable types must live in definitions. The $ref rules are super strict compared to JSON schema. $ref may only appear where a type expression is expected, and it must refer to a location inside the same document. So this removes an entire class of brittle location-dependent coupling and makes schemas locally complete and analyzable. And all the definitions need to go into the definitions section. To further make reuse possible, and that's kind of the inheritance model that many people are using, you can go and share common definitions through abstract types. An abstract type declares the structure, a common structure, but it cannot be instantiated, cannot be referenced directly. But it can be extended by other types to inherit the structure. So it's not polymorphism. There's no runtime subtype substitutions, purely structural reuse, share templates, not behavioral hierarchies. And as you can see with the dress at the bottom, you can create concrete types with the same shape as an abstract type by extending them without further constraints. Choice is a model for discriminated unions, and we have two variants. The first one you see here is the tagged form, where the selector really is a property name that identifies the active variants, and then those are mutually exclusive, and then each variant maps a concrete definition. And so this replaces effectively the use of one-off as a pseudo-union mechanism and produces a structure that's explicit, serializable, and predictable. And then there's also an inline choice, and that is for when you have a selector kind of mixed into the data structure itself, and that's modeling this. We have a base abstract type where the selector is living probably some shared properties, and then each variant can go and extend that base with the specifics that are applying to that selector, and that cleanly maps how many discriminated unions are modeled in different programming languages. There's an explicit notion of namespaces. Namespaces are a first-class construct. They exist inside of the definitions section and behave exactly like namespaces in programming languages. So they group related types and they disambiguate names. And they prevent collisions. And the root type and the top level effectively of the definitions collection, they live in the empty namespace, and then you can go and create namespaces inside of it. Namespaces are also the anchor point for controlled imports. An import is an extension, it's the first extension effective to the spec. And if you want to reuse definitions across files, you import those files and you map them into the definition section and potentially into a namespace. And then you treat them as if they were locally defined. And that eliminates all the path-based coupling issues that people are having with JSON schema. So these imported types can then be referenced with $ref. And this is very similar to what you know from C, C++ maybe. We have an include file where definitions are hoisted from a different file, but then ultimately act like as if they were local, and that's exactly the same model here. So we're separating referencing types from importing types through $import and $ref and have those separately. So that was an initial view at JSON structure. Right? It separates structure definitions from validations, names from patterns, reuse from location, and it keeps what works in JSON schema and removes what broke tooling and adds what real systems actually need. There will be more in future episodes, but that's what I had for today. Thank you for listening, and until next time.